All right, so if we hadn't had that snow day on Wednesday, February 1st, then we would have at least gotten started with this idea, constructing new functions from old functions. You can do that by sums, or I guess difference if you want to distinguish between addition and subtraction. You have products and quotients, and then composition of functions, which is super important. So let's look at these two, and we'll find their sum, their difference, their product, their quotient, and the corresponding domains. Well, this new function, f plus g, the name of this new function is f plus g. Its variable is x, and it would just be, the sum of them. There's nothing you could do to, combine those radicals. You can't combine those radicals in any way, so you're stuck. All right, the domain of this thing, well, I would need both 25 minus x squared to be greater than or equal to 0, and I would need x plus 1 to be greater than or equal to 0. Excuse me. So 25 would be greater than or equal to x squared, and taking square roots on both sides, I would have that 5 is greater than or equal to the absolute value of x. And that just has to do with the definition of the absolute value, which I guess I need to tell you about now. Now, I don't, it's not a problem here because, well, let me tell you the definition. So we had a definition for absolute value earlier in the semester. It was this piecewise defined function where you just use the symbol inside the absolute value if it was bigger than or equal to 0, but you tacked a negative onto the front of it if it was less than 0. And this is a perfectly fine definition of absolute value. However, there's another one which is that the absolute value of x is equal to the square root of x squared. This must be the case because the square root of a number is non-negative, and no matter what you put in here for x, even if it was a negative, squaring it would make it positive. So for example, the absolute value of minus 3 could be thought of as the square root of minus 3 squared. Well, that would just be the square root of 9, and you get right back to 3. We do not say that the square root of 9 is negative 3 or positive 3. We are not in elementary school where they failed to make the distinction between the principal root and these other roots. You will talk more about why the square root of a number is non-negative in complex. complex variables if you ever get there. So the square root of a number from now until complex analysis is going to be non-negative. And it just kind of like stems from this definition. You know, the thing that's true is that minus 3 squared, that's 9. But if I turn around and take this square root, you don't get negative 3 on both sides. You can only get the one number. We want it to be a well-defined function, so you just get the one number. Now, so then that's why when I took a square root on both sides right here, square root of 25 is 5, and the square root of x squared is the absolute value of x. And it says that the absolute value of this number is less than 5. Well, that would yield for you two equations, that x is less than or equal to 5, or a minus x is less than or equal to 5. And then this second equation would give you that x is bigger than or equal to minus 5. And this is what we expected. This function right here is just a half of a circle. It's just the top half of a circle with its center at the origin, and there's minus 5 and there's positive 5, and this is all of the domain values that that function would have, and that's expressed by it must be less than 5 or greater than minus 5. But you have those two stipulations, and then you also have that it must be greater than or equal to minus 1. So with minus 1 being right here, we have cut off our domain partially, and now you just have the domain from, that said minus 5, it should have said positive 5, sorry. Now we just have the domain from minus 1 to 5. Okay. And then they ask you for the difference of those two functions. It'd be the same thing, but with a minus symbol here. Same domain. What about their product? So let's recall here, f of x was square root of 25 minus x squared, and g of x was the square root of x plus 1. Then their product, f times g of x, well, then you could write it with one big radical. In fact, you're going to get some kind of trinomial underneath here. And you know, whatever that trinomial is, I don't know. It's probably not worth it to, it's certainly not worth it to multiply it out. In fact, you're going to want to factor it further. So 5 minus x, 5 plus x, and x plus 1, whatever that, I said trinomial, is that right? Yeah, no, I meant cubic, not trinomial, sorry. It's probably going to have 4 terms. So whatever cubic function this is, there it is, and now it's factored, and since it's factored, I can now know where that cubic function is non-negative. Think back all the way to week 1. I have to make my number line drawing. I have to put the partition points. The partition points are -5, -1, and 5. That's 3 unique roots for this cubic function. And all I need to do is figure out what happens here in this interval, because that's where 0 is at. And since it's 3 unique roots, this is just going to alternate. So when I put in a 0 for x here, here, and here, I wind up with a positive times a positive times a positive. So it's positive in this interval. Negative here, positive here. This is all the places where it was 0. So then my domain would be from -infinity up to -5 included, union together with the interval from -1 to 5. Then they want to talk about f over g. F over g, okay, it's a function of x. It would be the square root of, well, it's the square root of something over the square root of something, so it's just going to be one big square root. Actually, it's going to be more convenient for me to think about it as 2 different roots. So x squared minus 25 over square root of x plus 1. Then you can go all the way back to our first domain. We still need, it would still, that domain right there satisfies the property that the stuff under the radicals is not a negative number. But then I can't have the denominator be 0. So instead of it being from -1 to 5, where I include them both, I can't include the -1. So here's my domain. And this is the name of the game. That was the first example from assignment 10. Let's do another one. So now let's have f be 8 over x and g be 10 over x plus 10. Then f plus g no doubt it's going to just be 8 over x plus 10 over x plus 10. Now, I really don't have a reason to do any algebra from here and simplify that. I have no good reason to do it. I could. Maybe I want it to look like a single fraction. Whatever. I would want to do that if I wanted to know where this function was going to equal 0. I would want to do that because I would want to have a denominator, or excuse me, I would want to have a numerator. But to figure out its domain, however you add these two things together, that denominator is just going to be x times x plus 10. It's the same domain as if you had looked at each individual domain. Actually performing this addition is not going to help you learn anything in terms of the domain. So we just need that it can't be 0, and also it can't be negative 10. So it's all the real numbers except for 0 and negative 10. And if you were on a test that was written, handwritten, this is perfectly acceptable writing. On the homework, they're going to want from you an interval. It says use interval notation, so it would have to be from minus infinity up to minus 10, union, minus 10 to 0, union, 0 to infinity. And that's your domain. If you wanted to take the difference of these two functions, here we go. Everything else is the same. Now I've done the difference. If I want the product of these two functions, you're still going to have the same domain because they're both rational expressions. 8 over x times 10 over x plus 10. You have the same denominator here as you had here, because the denominator here would be x times x plus 10. There's no square roots or anything, so the domain here is exactly the same as we had right here, because they have the same denominator. But then they get to f over g, and then you're going to have to, then it'll be different. So f over g would be 8 over x and let me, I guess, write it like this: 8 over x and then 10 over x plus 10. So I guess I will type in the answer here to make sure that the people who wrote this software are thinking like I am, because you have the function f, you have the function g. They both are rational functions with domains that aren't the real numbers. The function f can't use 0, and the function g can't use negative 10. So automatically, any function I'm going to build in the future can't use 0 and can't use negative 10. Even if this thing would simplify to be 8 over x times x plus 10 over 10. Even though I have this simplification, my domain doesn't suddenly get back the number 10. Understand the difference between, so this is how f over g simplifies. But if I just came at you with this other function h and said that it was 8 over 10 times x plus 10 over x, well then its domain just needs to exclude 0. H would have a domain that's just all real numbers except 0. That's because it started out that way. But f over g was built from f and from g, so it would inherit the domain restrictions of both f and g. So yeah, I checked. We are on the same page. The domain of f over g is exactly this domain. All right. Well, now we can talk about composition. Composition of functions is fun, if you could call math fun, and I think I can. So let's look at if I had the function f of x, and it was 3x minus 2, basic linear function, and they would like for me to compute f of 2. Now, there's f ready to accept a value, and the value that you're putting in is this y value that you get from the function when you evaluate it at the x value of 2. Now, f of 2 would just be 3 times 2 minus 2, right? That's f of 2. So then f of 2 would be 3 times 2 minus 2 minus 2. Right? So it just says 3 times 4 minus 2. It's 10. That's composition. This idea of f of 2, f of 2, is, so I should have written it this other way. The correct notation for composition is this little circle, f circle f. This is the name of the new function, f circle f. We want to evaluate it at 2. And then the definition of how you would do that is to take f and evaluate it at f of 2. So if I have two functions f and g, then f circle g is a brand new function, and this is its name, and its rule, it's a function, so it has a rule. Its rule is f of g of x. So if we have that same f as previously of 3x minus 2, and then let's say that g of x is 5 minus x squared, then f circle g of x would have to be, I'm going to take my function g, which is right here, I'm going to substitute that whole thing in to f. So it'd be 3 times g of x minus 2, right? But that's just 3 times 5 minus x squared minus 2. And you can simplify it down and get the equivalent rule for your function. You'd have 15 minus 2 minus 3x squared. This is f circle g. And then you can evaluate it. So f circle g of minus 2, well, that's just going to be 13 minus 3 times a minus 2 squared. So you get 13 minus 12. It's just 1. Okay, what about g circle f? Well, g circle f at x, well, g was 5 minus x squared. So there's g. And it's waiting for me to put in here f of x. Then this indicates for you that g is the function that's on the outside, and f is the function on the inside. It's different than, it's the opposite from what we just did. So there's f here on the inside, and g is on the outside. And now I can simplify this guy. So it's 5 minus, and then I'll square this out. So I get 9x squared minus 12x plus 4, and distribute the negative and add the 5 and the minus 4, and you'd get minus 9x squared plus 12x, and then 5 minus 4 is just plus 1. So here is g circle f at x. You can evaluate it at whatever point you want to. Okay, maybe then you're interested in what happens to the domains of these composed functions. And just like before, that domain has to be inherited. You're going to inherit, so the new function is going to inherit every restriction that the previous functions had. Well, this f and this g have no restrictions. Their domains are every real number. So even if I do f circle g, I don't think there's not going to be some kind of restriction that suddenly comes up. F is the function on the outside. There it is. It's on the outside. It's ready to accept g of x on the inside. This is just some quadratic, x squared plus 18x plus 81. Its domain is all real numbers. G circle f. Well, here's g on the outside, and then it's ready to have f put in. That's just a parabola, vertex at the point 0, 9. Domain is all real numbers. f circle f. There's f of x, and it's ready for me to put in f of x. This is x to the fourth. Its domain is all real numbers. It's polynomial. Polynomials have domains all real numbers. And if I'm composing a bunch of polynomials, it's not going to suddenly become a rational. Let's look at if f of x was a rational, x over x plus 3, and g of x is 7x minus 3. Then f circle g, okay, would be 7x minus 3 over 7x. Now, G has no domain restrictions. It's a line. Its domain is all real numbers. F has the domain restriction that it can't be minus 3. So I know that my domain here is going to not be able to include minus 3. But then it also cannot include 0. Because 7 times 0 is 0. So there's my domain. It wouldn't, and so it's only 0. It wouldn't be something like 3/7, right? Even though, so the root of G is 3/7, but G doesn't have any domain restrictions, so then f circle G doesn't inherit any problems from G. What about G circle F? G circle F, okay, would be 7 times, I'm going to put F in there, and F is x over x plus 3. So I would have inherited the fact that the domain cannot include -3. But then there's nothing else. Then the composition doesn't also include another problem point, right? That's it. It's still this for your domain. Here's a good one, F circle F on that example with that particular F. Well, F was x over x plus 3, so we'd have x over x plus 3, and inside those parentheses I'm going to get to put f of x. Now, this composition might simplify in such a way where, in fact, I think it will simplify in such a way where it might not have a denominator with an x plus 3. So, but since it inherited that problem, it cannot have -3 in its domain. And think of it like this. All this says to you is, all this would say, So maybe if I wanted to evaluate this thing at -3, then I would have right here f of -3, and I'd have right here f of -3. And each of those are undefined. So then naturally the composition does not know what to do with -3. But once you do all the writing for the composition, this is what you would be left with. And so it can't include the -3, but I'm wondering if there's also going to be another number that cannot be included. Well, it looks to me like it's just a repeat of the -3, but we'll see. So I can add these. I can do the addition in the bottom, right? So here's my numerator, and then times 1 over 3 times x plus 3 plus x over x plus 3 . Okay, and then that would actually be able to be written like this. And the x plus 3's would cancel. And then you'd have x over 3x plus 9 plus x. So that's 4x plus 9. So you do have another domain restriction here, -9/4. Can't be -9/4. That's plain to see down here. I'm wondering if I could have seen it back up here. So, I see it. So, if I put my -9/4 there, you'd have -9/4 plus 3. Well, that's 12 minus 9 over 4. That's 12 minus 9 over 4. That's 3/4. So I would have this denominator of 3/4. I'd have a numerator of -9 over 4. But that's just the number -3. And so this part would come out saying -3, and then here's +3, and you get a 0. So -9/4 also cannot belong in the domain. I like that problem. Let's do, I guess, one more. Or a couple more. Here we'll have, I guess this is worth doing, F circle G circle H, where f of x is the function x minus 1, but is also h of x, and g of x is the square root of x. So I guess you could have just said F circle G circle F and then not had to worry about H. Okay. Well, if I have the function f way on the outside, then I'd have some stuff -1. And the stuff that goes in here is G circle F. But G circle F is just the square root of F. And there you are. Not much to it. Now let's talk about this function capital F, which is defined as x minus 6 to the 7th power. This type of stuff is directly relevant to what you will do in calculus, because you will have to be able to recognize how to take some function and decompose it into these other two functions. Right? So I would like to identify the function f and the function g such that f of x is equal to f circle g. And when I'm doing this in calculus, usually I will not use x in both of them. I'll say f of star and then g of x. And it seems to make it easier, because then I can see that f of star just needs to be star to the 7th, and g of x is the x minus 6. And then there's not so much x's floating around, because x is busy. And then now if I take g of x, the idea here is that star is g of x. So g of x to the 7th is f of g of x, which is exactly what we were wanting to do. Now, don't use the star notation in the homework. They won't understand that. They're asking you for f of x. So you would just say x to the 7th. At the end of the day, this is just a symbol. And as long as you have the matching one over here, then it makes sense. It doesn't matter if you used a smiley face, picture of a duck, or, whatever. They just need to be the same. And I guess one more of those. We have the function capital G of x being 1 over x plus 8. And I would like to identify what f in little g would need to be so that f circle g is capital G. Then f of star would have to look like 1 over star, and g of x would just be x plus 8. And now you're done, because you could write that f of x is just 1 over x. G of x is x plus 8. All right, then there's a couple of word problems at the bottom of the homework. Let's see. I'll do this last one for you, or get it set up. A spherical weather balloon is being inflated. Okay. Here's my spherical weather balloon. And it's being inflated. It's got some radius, I presume. The radius of the balloon is increasing at the rate of 8 centimeters per second. So R, how would I say that without calculus? I mean, you would normally say dr dt, which is the rate. I'll just say that the rate is increasing at 8 centimeters a second. Express the surface area of the balloon as a function of time. And at time 0, it had area 0. So the surface area, if I'm not mistaken, of a sphere is 4 pi r squared, I believe, because the volume's 4/3 pi r cubed. Yeah, this is the surface area. I don't want to tell you wrong. Let me just double check. Surface area of a sphere. Yeah, 4 pi r squared. So that's the surface area of a sphere. But this would be just at one particular point in time. Okay. And it says that the radius is increasing at a rate of 8 centimeters per second. So we could write a little linear function expressing what that radius looked like over time. And we can see that in this writing of the surface area of the sphere, the only thing it depends on is the radius. So it is a function of r. And if that radius is depending on time, then I'm pretty sure it would be this. So when t is 0, the radius is 0, and when t is 1, the radius is 8. This is a linear function. Then I can talk about S composed with R. But I don't want to write this. I don't want to write this. I just want to say, just going to substitute that in, right? Actually, substitute it in over here. So that way S of t would be 4 pi times 8t squared. And then you'd have 64 times 4, which is 256. 256 pi t squared. There we go. All right. The last section that we would have covered, or the next homework, I should say, which is assignment 11, we will cover Monday. That's what I mean to say. All right. And also on Monday we'll cover whatever else we need to having to do with this stuff. All right. So talk to you later.